Okay, so these were basically the structural aspects of this, and now we want to get a little bit closer how one can actually use these things then for designing general first inference algorithms. And the first thing that we require then, if we want to talk about specifically free-form variational inference, is that we need to introduce this notion of a mean field approximation. And this is another thing that has a somewhat strange name, mean field, because it sounds like something like a field in physics and so on, like variational free energy and so on, but means something fairly, first of all, specific but also straightforward, because what it means is that instead of using a completely arbitrary variational distribution, we use a variational distribution that factors into sets of random variables. So, for example, instead of using, before we go over this notation, instead of using a two-dimensional variational distribution Q of x and y, we restrict to the class of variational distributions that can be formed by the product. So we assume that x and y are independent random variables. So what this mean field approximation then always brings to the table is it's easier to do variational inference with it because it's easier to do the computations, and we have good solutions. But we also always assume this form of independence in the posterior, which is of course not necessarily correct. So for example, if you have a Gaussian posterior, of course you can have in a Gaussian posterior, you can have covariation. So if this is your isocontour of a Gaussian, if you approximate this by a factorized distribution, you will of course always approximate it by such a round thing, which is of course wrong because it's not completely the correct posterior distribution. However, in a Gaussian case, you don't need the whole variational inference anyway, because if it's a linear Gaussian model, you can just do things analytically. So with this kind of informal introduction, now a little bit more formal and more general, what a mean field approximation is. So if we talk about our latent random variables, Z1 to Zn, then we can of course partition these into S mutually exclusive subsets, so that if we combine these subsets, so if we look at their union, we have again our complete set of random variables, and we don't have any random variables in different sets of the partition. So this is this typical partition thing. It's very simple to think about, but a little bit annoying to write up. So a partition, for example, if we have Z1, Z2, Z3, Z4, then one partition would be Z1 and Z2, and Z3 and Z4. So here we would have three subsets, and the first has the first two, and the second ones have the second twos. The idea of the mean field approximation is then that the variational distribution factorizes over these subsets. So as we've seen before, if we have two random variables in Z, Z1 and Z2, and we assume a mean field approximation, the only way that this can factorize is into Z1 and Z2. If we have three, we could assume full factorization, or just QZ1, QZ2, QZ3, or partial factorization QZ1, Z2 times QZ3 and different ones. And this assumed or defined factorization of the variational distribution is called mean field approximation. It's just the name. And don't ask me about the story about the name, so it has to do with physics and the thing that this independence and factorization property in physics is for some reason called mean field. Whatever. If somebody knows why exactly, that's fine. I think the name is a little bit annoying. I mean, it's still a name like variational free energy that is not that clear. I think elbow is a better name because you get completely rid of this physics analogies and so on. And here it would be better to call it the factorized variational distribution assumption or something like this, because that's what it is. But it's even if you read the Bly articles, so the more modern articles on variational base that talk about the elbow, they still use the term mean field approximation. So I also use it. And then if you make this assumption that there's this factorization in the variational distribution, the whole thing is also then sometimes called mean field variational inference. And of course, because you assume this independence in your approximate posterior, that's not something that you necessarily want. So of course there are developments to get rid of this mean field approximation. So common mean field approximations that you sometimes encounter are things like full factorization, so that each latent random variable has its own factor in the formation of the variational distribution. Or at least you have, if we now talk about the coordinate ascent variational inference, you at least have a binary factorization so that you have one subset, for example, 4 of your random variables, and here 6 if you have 10 random variables in total. It always depends a little bit how the factorization is done on the specific model and how then the calculations turn out, especially if you do certain analytical calculations, how they are simple so that you can actually do them. Yeah? So this whole mean field approximation business is to ease the calculation of integrals in the end. Okay, but here we just want to establish this term of factorizing the variational distribution. Questions? No. No. And of course, mean field variational inference neglects potential non-independencies in the posterior. Good. Based on what we have so far, so the log model evidence decomposition and the mean field approximation, we can now say what we mean by free-form mean field variational inference. So we assume we have this probabilistic model. We have observable random variables, modeling data, and latent random variables, modeling parameters or states. We assume we have a variational distribution about which we specify nothing. So we just say it's a distribution or density over Z, and we only assume that it factorizes in a binary manner, or at least binary manner, over one subset of the random variables ZS, and the other subset, this I always denote here with this without S, so this should be the remaining ones. So if, for example, if the M is 10, then this could be 1, 5, and 7, these random variables, and this would be 2, 3, 4, 6, and 8, 9, 10. Yeah, so it's just this binary factorization. Now, if we have this factorization and this probabilistic model, then free-form mean field variation inference rests on this result, namely setting the QZS factor in this factorization to the exponential of this integral, namely integrating the log joint distribution over the other random variables which are not in this partition, integrating this, taking the exponential and normalizing appropriately maximizes the elbow. Yeah, so again, we discussed that we want to maximize the variational free energy, and free-form mean field variational inference tells us how we can maximize the elbow, at least with respect to one partition of this, and it tells us if we want to maximize the elbow with respect to this partition here, then we need to compute the integral of our probabilistic model, which we know, under the other distribution, take the exponential and normalize so that it's, there's a typo, QS, so that we have a probability density. Now, of course, you can, by exchanging ZS and Z without S here, immediately then also maximize with respect to the other partition or the other set of random variables. So that's what I'm saying here, and we will see an example. The magic in a way here is, or it's not magic, but the crucial point, and why it's also called freeform, is that you're not saying this distribution over ZS is a normal distribution or a gamma distribution or beta distribution, but the functional form, so the specific density form, falls out of this integral. Yeah? And it actually does in simple examples, but it requires evaluating analytically these integrals. And this then also determines a little bit how you choose the partitioning. So of course you want to have here these integrals, you want to be able to compute them analytically. So it makes sense to take these partitions in a way that you actually can do that. If you if you have to compute this integral, but you don't know how to do that, then of course it doesn't help. So yeah, so that's one thing. Another thing is that this freeform mean field variational inference is a little bit like analytical maximum likelihood. So in simple examples, like for example finding the maximum likelihood estimator for Gaussian, yeah, you compute the partial derivative of the log likelihood and you solve, and you see it's the mean. And the same for freeform mean field variational inference. If you, for example, try to find in a specific model the variation distribution for to approximate the posterior distribution of the mean of Gaussian, and you have another distribution over, let's say, the variance parameter, yeah, then it works. But as soon as you have kind of a model that is a little bit more involved and is not of this textbook style, then often free-form mean field variational inference doesn't work anymore, and you can do other, and you will do other forms of variational inference. So it's a nice textbook kind of theoretical thingy. Also a way, of course, the way that things started. So often, of course, yeah, you can calculate things, and then you say, okay, now if the model is more complex, I cannot calculate this anymore, but then I can do the calculations maybe like numerical maximum likelihood in some numerical way. Now, where does this formula come from? this formula comes from variational calculus. So this is the remnant of variational calculus that you see in variational inference, because maximizing the elbow, so which is a function of functions as we've seen, with respect to that, if the elbow is a function of this product, variational inference, can be shown using methods from variational calculus to come out to this. I'm here showing, based on some tutorial on variational inference for linear regression, I'm not using variational calculus to show that this holds, but show it in a different way. So the question is, why does this maximize the elbow? And one way to show that is to say, okay, if we have the evidence lower bound as a function of our variational distribution now can be written as this product because we do this mean field approximation, then we can reformulate this evidence lower bound as the negative KL divergence between this part of the variational distribution, so this partition QZS, and this thing that we've just seen at the solution. Now, if we want to, and this is a negative KL divergence, and KL divergence is always positive. So if we want to maximize now the elbow with respect to QZ, there's a constant which is not depending on QZ. If we want to maximize it, well, then because it's negative, we just set QZS to this. Then the KL goes from, I don't know, -100 to 0, and we have maximized the elbow. Yeah? So the crucial thing here is the rewriting of the elbow in this way. Such then it follows immediately that we maximize the elbow by setting the QZS to this. Now, this is what it says here. So maximizing this negative KL divergence by setting QZ to this maximizes the elbow with respect to QZS. Now the question is, why can we rewrite the elbow like this? And this is this. So I'm not going over that in detail now. So yeah, go over it. It's fairly straightforward. It's basically decomposing the elbow. So it starts with the elbow definition and putting in the partition over the random variables, and then working towards the reformulation in this form, while at certain points defining certain constants. So, and it's just taking apart integrals and sometimes integrating over a probability density function and so on. So work over it, let me know my typos. It works. But yeah, it's a little bit tedious, but it's also not hard. That's the good thing. So it's relatively straightforward, and it's definitely much more straightforward than to introduce variational calculus and how to do constrained maximization in variational calculus. Because if we maximize the elbow with respect to the probability density function QZS, then of course we have the constraint that it's a probability density function. So we would have to look into variational calculus under constraints. We did this in this 2014 paper, that's all in there, if you're interested in the variational calculus aspects. But then if you apply variational inference, you often don't need to re-derive this thing here, but you use it. And often you might not even use this because you're not doing free-form variational calculus. Yeah, so basically what we've said is that we can maximize the elbow under this mean field approximation with respect to one part of the approximation, so the PDF over CZ is by using this. I also said that, of course, by reversing the roles of QZS and QZ without S, we already find the maximization with respect to QZ without S. Now we can put this together, and this is what they call these days coordinate ascent variational inference, or KV. And that's what is on this slide. So this now uses the mean field approximation and the maximization with respect to one of the partitions in the following way. So we start with a probabilistic model with observables and latent random variables. We assume that we have a variational distribution, and it factorizes in a binary manner, and then we can use this algorithm that iteratively maximizes the evidence lower bound, or the LBOC. So we start, this is now getting into algorithmic businesses, so we start with some form of Q0, although this, one can discuss this. Actually, maybe I should revise this because this can lead to confusion. So the first Q0, actually, we don't need to initialize, but we can get it just from applying this. So we don't actually need to initialize Q. This maybe it's even a mistake. So we don't need to initialize Q0, because the first Q0 we get from doing this here. We need to have certain things about QZS. I think one would have to look a little bit into the details of an example to really make this clear. The problem is between initializing things without making, by leaving it still free form. Yeah. So I have to put a question mark here for myself, because you cannot compute this integral over ln p x z and q without s without completely not saying anything about QZS. But then there I have to think a little bit about. Maybe we go a little bit deeper into the example next time than I intended to get this clear. But then we would always have some initial Q. So we have a Q over the other one, so we can derive the next. We need an initial one. We derive the next variational distribution over ZS by applying this formula. Yeah, and it's still free form in the sense that we don't say anything about the form here. We let the thing is, and this is why I sound a little bit confused right now. If you actually do this for these examples, then you're in the very beginning, you're fairly quickly sure that this partition is, for example, a Gaussian or a gamma, and then it comes down to parameter updates. But formally, actually, what you do is that you are surprised every time again that it's again a Gaussian. I think that's maybe the way to see that. So you can also start, for example, here. Now you need something here, but you start somewhere, and then each time you don't say something about the form here. You compute this integral. Of course, you need to know something about QIZ without S. And then, surprisingly, the integral comes out as a Gaussian density, for example, or gamma density with certain parameters. And then, once you have done this, you reverse the roles. So you put this that you computed here, you put this in here, again compute this integral, and let the integration surprise you with the functional form of qi plus 1 of z without s. And in this way, you go back and forth. So you always do with respect to that and with respect to without this, and let the functional form of these distributions fall out of these two equations. About this initialization, because you have looked into examples recently, so I hope maybe not yet. Do you have anything to add?
I don't know the answer to your question either. I don't know what initialization. So much into the free form.
Yeah. So the way it's usually portrayed is it's a little bit different. So it's not immediately portrayed in terms of this algorithm, but it's just portrayed in terms of you compute the integral and hence this distribution without thinking about an algorithm, and then you have the functional form, and then you put it into an algorithm. Yeah. I guess the thing about the initialization is a little bit something to discuss. The important thing is here that you don't want to say I'm using Gaussians or I'm using gammas or betas or whatever. You want to say the functional form comes out of this integral. And then you always reverse the roles and always compute these integrals again. So if you look into the old 2014 paper, this is where we go a simple example bit by bit and do all these derivations. The derivations are relatively long because you have to compute quite a few integrals. So maybe next time I look into how we initialize things there and try to clarify that, but I still don't want to go over all the derivations because it's horribly long. It goes on forever. But this is the more important thing about, forget about the initialization, the more important thing is that you always maximize with respect to one part of the partition and then with respect to the other part of the partition. And in this way you, for example, if you would just view the elbow as a function of two coordinates, you first go maximizing like this, and then you go maximizing like this, and then you go maximizing like this, and like this. So you do this coordinate ascent. And then in the end, you check always whether your elbow is still increasing. If the difference, for example, that's one way to check whether you reach convergence. If the elbow is smaller than some convergence criterion, you stop the whole thing and then use your final variational distributions as your, in their product, as your approximation to the posterior, and your final elbow as the approximation to the log marginal likelihood. So yeah, so maybe let's have a look at that before I say some final words about freeform. So if we have somehow already such that we can talk about our variational distributions and we can put them into the elbow, then we can evaluate the elbow and the KL divergence, and we would start here. Now, what we then do is that we update the first thing. This maximizes the elbow a little bit, gets the KL a little bit smaller, and then in the second step we evaluate or maximize with respect to the second part of the partition, gets elbow even larger and KL smaller. And then in the end we would have hoped to have pushed elbow most of the way here so that the KL divergence is 0 and the posterior is well approximated. But for example, if you think about if you have a posterior that has correlations, so this 2D Gaussian, you will never really get the KL divergence to 0 in this case. So there will always be a remaining KL divergence, but you have your best approximation. So again, this is the general idea of doing this coordinate-wise ascent. Thing about freeform, like I said earlier, is it's mainly of theoretical value, but there is of course of value. But it's really involved in terms of the analytical derivations, because you have to compute many integrals. And if you're lucky, you can compute the integrals. And for these simple linear cases, you can actually compute the integrals exactly, and then you actually get these distributions. However, often if it's more interesting models, you may not be even able to compute the integrals. And it's also, and this is what a lot of people, and why this is a little bit involved, and there are not so far many toolboxes. I mean, there are some toolboxes, but it's analytically involved. You have to sit down and do the math to do variational inference, like in the Penny papers. So they sit down, did the math, and then they have this algorithm. But because it's like this, of course, people came up with other ways to do a variational inference. And one way that is definitely a way that is popular in brain imaging, and also beyond that, is to, instead of having the functional form of the variational distributions fall out of this central theorem here, to just assume from the very beginning functional forms for the variational distribution. So again, you do a mean field approximation, and you assume that your variational distributions are of specific functional form from the very beginning, without having to do any integral, just by saying, okay, I want my one factor, I want this to be a Gaussian. Maybe I want all of my factors to be Gaussians. And this is called fixed form variational inference. And this starts out from the same setting. It usually, of course, then uses variational distributions of specified parametric form. And then the problem becomes, of course, about parameter updates. So you assume that the variational distribution is Gaussian all the time. And if you want to do a coordinate ascent, or if you want to do coordinate ascent variational inference, you have to update these parameters. How do you update these parameters? Well, the crucial thing is, if you have the functional form for your variational distribution, then the elbow can be evaluated analytically or approximated, and be viewed as a function of the parameters. So what you essentially do is that, instead of viewing this whole problem as a variation calculus problem, where you have this functional elbow that you would need to maximize with respect to a probability density, because you know the variational density, you have defined it, you know this, you can just solve this integral, or approximate this integral, and then view the elbow as a function of the parameters of the variational distribution. Yeah, and then you have a function of numbers, namely parameters, which still can be complicated. So, for example, vectors and covariance matrices in the Gaussian case, but you don't have a functional or variational calculus problem anymore. So you don't need to maximize with respect to functions. And that's the basic idea of fixed form variational inference. So you say, okay, I assume for my Q, I assume, for example, a Gaussian. This I have specified because it's my model. Then I evaluate this integral, and then I turn my elbow as a function of probability density into a function of only the parameters. And then I use then I maximize this function here, which corresponds to my elbow with respect to the parameters. And the parameters, of course, the parameters of the variational distribution. So if you have maximized this function, which represents your elbow, in the end, you have also found the parameters for your variational distributions. So, for example, you can make, or what is happening, at least in neuroimaging a lot, is, or not only in neuroimaging, so this is bigger than neuroimaging, but we all know from neuroimaging is that we make the assumption of a Gaussian distribution, and this is then called variational Laplace, and it's the stuff that's in SPM. It has nothing to do with the Laplace approximation as we discussed last time. Yeah. So these are the two main basic forms. Of course, in fixed form variational inference, you can also use the mean field approximation. So this is essentially the general story about variational inference until, let's say, 2010 or so. So there was free form and fixed form. With fixed form, you still have to do some analytics because you have to evaluate this integral. And then what happens is that sometimes you only even approximate this integral. So this algorithm is not properly evaluated, and the question is how good that is. Now, I don't think I want to start with the examples today. We then do that next time, but I'll tell you what is currently happening. So here are two examples for free form and fixed form variational inference, which we will discuss next time a little bit. Now more on the bigger picture, what's currently going on in variational inference. So one thing that I already mentioned is that there is some movement, or a big movement actually, to combine variational inference, so probabilistic inference in the variational settings with neural networks. That's this variational autoencoder business. So Kingma and Welling, they had this 2014 abstract, which actually just discusses variational inference, and at one point says, and here this likelihood we could use it's quite funny because it has so little to do with neural networks. They need a likelihood in this. They need a likelihood, of course, if you specify your model, and in this likelihood they use a hierarchical Gaussian model. So they use something that essentially comes down to something like this. This is normally distributed roughly, and then you have x, and x is distributed with some matrix here, some a theta 1. So they have this linear transformation, maybe they have two levels or so on, but then they call this neural network, and because neural networks are of course linear transformations with some non-linearities in there, and maybe they even put a log or a logistic function on the final output and so on, so that's a little bit more like a neural network, but essentially it's a hierarchical Gaussian model for the likelihood, and they call that neural network. And on the one hand, I think it's a little bit ridiculous to now give a new name and then reinvent variational inference, but on the other hand, so on the one hand I think it's really cheap to get cited a lot and have and combine neural networks with variational inference. On the other hand, I'm also quite thankful that they did that, because all the neural network people then learn about variational inference, and variational inference survives. So that's the good news. That's variational autoencoders. We will talk in the summer term and scan a little bit about variational autoencoders once we discuss neural networks there. Other thing, and this is now more related to what we've seen today, is stochastic variational inference. The problem with both fixed form and free form variational inference is that you have to do a lot of analytics. You have to evaluate integrals, you have to compute gradients if you want to use a gradient-based optimization scheme, and so on. So there is movement to get away from having to do lots of math and replacing doing the math, for example, with sampling techniques. And stochastic variational inference is roughly, I mean, it's not quite that, but it, for example, for the gradients, instead of evaluating the gradients analytically, it uses sampling techniques. And this is more like a general theme which tries to combine the ideas of variational inference, trying to throw out all the mathematical derivations that you need to do, and replacing them with numerical techniques. And of course that's makes certain sense, of course, because sometimes, first of all, it's very tedious to do the derivations, and it's also not very general purpose. Yeah? So that you have this general purpose idea of doing variational inference, but then if it comes down, it's fairly specific to your specific model, and you have to do the analytics there. So that's one theme. So stochastic variational inference and combining essentially sampling with variational inference. And then the last theme is that because it's such a novel paradigm in statistics, to actually study the properties of variational estimators. And this, of course, then, from my opinion at least, depends a lot on what kind of specific variational inference procedure you have in mind. So if you talk about fixed form variational inference, where you only approximate the elbow, well, then maybe things don't quite work. If you're using free-form simple variational inference, then it might work because you can build on other insights. So, for example, variational inference is a generalization of the expectation maximization algorithm, and expectation maximization is known to converge, and also the estimates of that have been studied because it's a maximum likelihood estimate. So you can build on that. So this is another topic that's currently going on. So it's at this point. There are many variants of variational inference, and mostly then applied in specific examples, and we will look at some examples next time then. But it's not, so if you, to answer the question, what is better, is not really possible, which is interesting because it's an emerging, ongoing field of statistical research. Yeah, so that was kind of the big picture of variational inference, which stays like that. But I think it's helpful that we look a little bit at the examples, so to for you to get a little bit more of an idea what it means in practice then, and how things look in practice. Good. Questions?
In some of these packages, they have something implemented what they call black box variational inference. You have that refers to the second one.
That's, yeah, I think so. The Hoffman and David Bly, so that's David Bly. Yeah, so this, I think behind this is some stochastic variational inference, and here Nadine Spichalla, another master student, she also used this black box variational inference for her master thesis. Yeah, so that's the aim there in a way, so that I find it a little bit weird, but anyway, so the aim there is to have black box variational inference where that you basically, where you don't have to do any analytics, you just apply this thing and it does its thing, and it's a black box and you don't look inside, you don't want to know. Actually, I'm not, when I will work on Nadine's thing, then I think I will look a little bit into this black box variational inference, which is, I think, the stochastic variational inference. But the aim there is, of course, also to, like always, if you're doing some research and in methods, and you actually want people to also to make your methods important in the sense that people use it, the easiest way to do is to develop a toolbox and then go and sell this toolbox, say it's doing awesome stuff, use it, then they cite you, and you have some purpose in developing this method, because you can always say, oh, well, they will use it, so it's important. So that's the standard way of academic career kind of building. Yeah, and on the one hand, it's good because it keeps the interest in variational inference up. On the other hand, it also encourages, again, a lot of toolbox use, which, yeah, one can have different opinions about. Any other questions? No. Good. Then let's stop here and then start in the Übung with more down-to-earth Bayesian inference in the conjugate case.